Hi everyone, I hope we are streaming and my audio is there. The first check that I need to do is that whether you guys can hear the audio of this video or not. Okay, so let me check that.
Never be doing any of this in production. It's really just done for pedagogical reasons because it allows us to not have to deal with these n-dimensional tensors that you would use in modern deep neural network library. So this is really done so that you understand and refactor out backpropagation and chain rule and understanding of neural network training. And then if you actually want to train bigger networks, you have to be using these tensors, but none of the math changes. This is done purely for
Let me check.
done so that you understand and refactor and chain rule. It allows us to
Okay, so let me check that.
never be doing any of this.
I hope we are streaming and my audio is there. The first check that I need to do is that whether you guys can hear the audio of this video or not. Okay, so let me check.
N-dimensional that you would
Yep,
use in modern deep.
so it's coming. The audio is coming crisp. Um, Similarly, as yesterday, we will be starting with question. So we have this series of understanding Andrej Karapathy's zero to hero neural networks, in which will be going through all of his videos. Okay, and the process is like whichever terms or concept will be unfamiliar to me, I will be writing about them in this manner where it can be a GPT chat or Gemini chat or anything, but anything that has helped me to understand that particular concept. So I'll be linking that over here and I'll be also summarizing that what is what does it actually means. Okay. So yesterday we we were able to watch only up till 6 or 7 minutes. We were also stuck in some sort of technicalities of streaming. But now today we hope that we can cover more. Okay, so whichever concept that I will be not aware of will be would be I'll just can I just toggle this? Yeah, and then I can put all of this over here. So, yeah, this is part one, 18th of January. Okay, the second part is part two, that is 19th of January. Okay, hours were 1 hour only. Okay, okay. So, this is how we are going to approach this, where we will be watching the video for 1 hour straight. Okay, go through what he is telling, understand in deep what all of this actually means, leverage the use of LLMs in understanding these concepts deeply, and comparing these concepts with real world analogies has really helped me to understand them with better clarity. Okay, so I'll be doing this only. Can I just, yeah, this is better. Okay, so let's start. I have this timer with me. Okay, and unlike yesterday, where there was no audio, today I have figured it out, and you will be able to hear Mr. Andrej Karapathy's beautiful voice. Okay, so shall we start? Yes, sir. Okay.
for efficiency. This is done to make it the stage.
So before starting up, I just got this in my mind that before starting up, let's revise what we did yesterday. Okay. So yesterday, Mr. Karpathy told that he has built a micrograd library which is of 150 lines of code, and this 150 lines of code has the has the ability to create and build a neural network. Okay, so first of all, he has created this micrograd library, and it is very simplified library which demonstrates neural networks through simple scalar calculations. Okay, so for those who are non-tech, okay, or kind of new to this, I have written what is library, what does actually a library means in coding. So to give a high level overview, you can think it as a toolbox. Okay, a toolbox that contains different tools for performing specific operations. So let's say if a mechanic brings a toolbox with him, okay, for something for tweaking or doing some operations in car, he will need some tools. Okay, he'll need some screwdriver on or then and that sort of stuff. Similarly, in the world of software development, whenever you want to perform some specific operations, you can either do it manually through loops and all that primitive methods and primitive data structures, but for faster approach and for efficient approach, you can directly use this functions that are existing in libraries. If I compare this to a real world analogy, you can always open a screw with your nail. Okay, let's say if you have a big nail, you can always open a screw, but it will be tough. Okay, it will be tough. It will be a lengthy process. It will be a very maybe there are some efficiencies also less. Okay, but with screwdriver, it is it is very intuitive, and it is kind of comparatively faster than this nail method. Okay, so basically, this functions and methods in libraries do this only where the software developer can leverage the different functionalities of libraries. Okay, so Micrograd is a library for building neural networks, and it has tools. Okay, you can compare. I'll just reiterate. Micrograd is a toolbox to create neural networks. Okay, and which has tools eh, which are called functions or methods that help in creating this neural network. Okay, so this is done. Okay, afterwards, he said about backpropagation. Okay, so what is backpropagation? First of all, I used to think is backpropagation was part of neural networks, there was a direct relation between backpropagation and neural networks. Means backpropagation was dependent of neural networks, but it's not true. Backpropagation is a fundamental concept, one of the fundamental concepts in mathematics, where you go back through the whole you know, let's say you have some mathematical operations initially, and you get to the output, but from output how you can get back to the original input is basically back propagation, and that is a fundamental concept used in mathematics. What Why this back propagation is helpful in neural networks is because it helps us to calculate the loss function. Okay, it helps us to calculate the loss function. Basically, how that, let's say there are two inputs A and B, and after some multiple operations you get to G. I'm reiterating is example only. So there are two inputs A and B, and after some performance, after some operations, you get to the output G. Then back propagation will tell you that how much variance in the value of G will be there if A, if the value of A is increased slightly or decreased slightly. Okay, so this gives us some sort of our relation between G and A. Okay, so how you can tweak the value of A to get the desired result G. Okay, that is the only knowledge I have and information I have right now. I'm definitely very hopeful that I'll be able to understand it more deeply. So that is back propagation. Then he used the word tensors. So I actually wanted to know what are tensors in neural networks. If I want to say in this one line, then tensors help to organize data. Okay, because in machine learning, there are times where there is a relation between multiple data points. Okay, there will be let's say if you have an image, then if you image has aspect ratios, okay, 28 cross 28 or 1920 cross 1080. Okay, so these are the pixels. This is the width and height of the image. But in order to this, okay, in relation to this, each pixel has some value of RGB. Okay, so that is also we need to consider. So we got here, what we got here is a three-dimensional, vector, which is called as maybe 2D tensor or 3D. Let me just open this. So yeah, it is called as a 3D tensor. Okay. So in machine learning, performing calculations is performing calculations with individual points is quite difficult, and that is why these tensors help to organize this sort of similar dimensional vectors. Okay, so for example, if there is only one data point, then it is called 1D tensor. That is, okay, if there is a row of tensors, then it is called 2D tensors. If there is a row and they are arranged in a column wise manner, then it is 3D tensor. And if these tensors are stacked on each other, then it is called 4D tensor. A simple analogy we used here with the help of ChatGPT was pizza boxes, right? So consider a pizza as a single data point. Okay, so when a single pizza slice is placed inside a box, then it is called as a 1D tensor. Here, the tensor is equivalent to the pizza box. Okay, why? Because pizza box enables and helps us to organize this pizza and its related operations very efficiently. Okay, it helps us to manage operations, to perform operations on this, because you cannot just give four slices of pizza to everyone. You put them under in a box. Okay, so that box helps us to organize that slice point. To have that box helps us to organize that pizza size slices, right? Similarly, tensors helps us to organize data points. Now, if there is a single slice of piece, you can compare it as a single data point. Okay, now I have arranged these pieces, slices of pizza in a single row. Then you can consider that this as an image that has only single row, single pixel that is arranged in one line. Okay, it can be, let's say, this one. If I'll be able to consider this, okay, this, if I go many, it won't be visible. Let me open some. Yeah, let me open some image. Okay, let's just, if I go, okay, see. So if you consider this right now, okay, this one you can consider as a 1D tensor. Why? Because the pixels are arranged in a single line manner. Okay, so this is a 1D tensor. Suppose instead of this boxes, there are pizza slices, right? So it will be a 1D tensor, but the box here helps us to pack these data points and perform operations on them collectively. Okay, you don't need to add some value to this, then this. No, if I want to add this or this set of pixels to this set of pixels, I can directly add this both boxes. Okay, so that is a 1D tensor. If I can just increase this is a 2D tensor because the pizza slices are arranged in a row wise manner and in a column wise manner. That is why this is 2D tensors. Now there are times, see, this every pixel here has some value of RGB. Okay, that is a fundamental thing. Each of this pixel is a combination of red, green and blue. Okay, these three values. So every pixel has this value plus the RGB value. Okay, so if I consider this structure, it has pixels arranged in a row wise manner, it has pixels arranged in a column wise manner, plus there is a certain value attached to each pixel, and that value is RGB. Okay, so we have to take that in consideration also. Okay, so that is why this is called as a 3D tensor. Okay, I have demonstrated here as, you can consider this. If I want to extend the pizza analogy, you can consider that now that pizza slice has three layers: cheese burst, toppings and some sauces. So this each pizza slices is made of these three different components. So we have to, if I want to perform uniform operations on it, I have to consider these three layers, right? So this is a 3D tensor. Now if these 3D tensors are stacked over it, okay, stacked, let's say I have two, for example, I have two areas, area A and area B, but area A has this set of pizza boxes that needs to be delivered. Then I'll just stack these 3D tensors, I'll just stack these 3D tensors over each other and put a stack put a box, make a bigger structure and send it to our area A, area 1. Okay, then I'll prepare different set of pizza boxes and send it to area 2. Okay, so in a way, what actually happens is this boxes has allowed us, they provide us the flexibility to perform operations on all of this on pizza related things. Okay, similarly tensors have also helped us organize these data points such that the GPUs can perform multiple mathematical operations over it. Okay, so if they were not if tensors were not present, it would be really tough for anyone, for even GPUs, for not anyone, for GPUs to perform operations on single data point. Okay, so this is what we have understood yesterday. Okay, I know it was just 5 minutes uh, uh, mm, of this Andrej Karapathy's video, but yeah, we learned actually a good concept yesterday. Okay, so for your better understanding, I have written this all of this is written in this Notion file. Okay, even the concept of pizza is also here. And just to give you guys a heads up, I'm being able to write these analogies with this much speed and this much quality with the help of GPTs. Okay, I would have not it would have not possible without this. Also, yesterday what I did is, I upload that I have you know I have upload a podcast related to this. Can I upload yeah, file? Okay, choose file. This it's a TensorFlow. So sorry, it's a podcast that I created of this whole concept in notebook from notebook LM. So yeah, I'll be posting this also. It's a good file. Done. Upload or embed a file. But I upload. So the maximum size is 5 MB. Okay. Okay. Okay, bro. Not a problem. Not a problem. Can I just go here and share this copy link and no. Uh, 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 uh. Yeah, this one only. Yeah, works better. Works better. Okay. So now I'll be proceeding further. Let's start this 1 hour timer. Okay. And let's freaking go.
Is that, as you see here, Micrograd is a scalar valued autograd engine. So it's working on the level of individual scalars like -4 and 2. And we're taking neural nets and we're breaking them down all the way to these atoms of individual scalars and all the little pluses and times, and it's just excessive. And so obviously you would never be doing any of this in production. It's really just done for pedagogical reasons because it allows us to not have to deal with these n-dimensional tensors that you would use in modern deep neural network library. So this is really done so that you understand and refactor out backpropagation and chain rule and understanding of neural network training. And then if you actually want to train bigger networks, you have to be using these tensors, but none of the math changes. This is done purely for efficiency. We are basically taking all the scalar values, we're packaging them up into tensors, which are just arrays of these scalars. And then because we have these large arrays, we're making operations on those large arrays that allows us to take advantage of the parallelism in a computer. And
So yeah, this is what we understood, that tensors are nothing but they are just an array of the scalar values, and it is quite easier to perform operations directly to this scalar value or this to this arrays, okay, instead of scalar values.
All those operations can be done in parallel, and then the whole thing runs faster. But really, none of the math changes, and the operations can be done in parallel. You take advantage of the parallelism in a computer, and all those operations can be done in parallel, and then the whole thing runs faster. But really, none of the math changes, and that's done purely for efficiency. So I don't think that it's pedagogically useful to be dealing with tensors from scratch. And that's why I fundamentally wrote Micrograd, because you can understand how things work at the fundamental level, and then you can speed it up later. Okay, so here's the fun part. My claim is that Micrograd is what you need to train neural networks, and everything else is just efficiency. So you'd think that Micrograd would be a very complex piece of code, and that turns out to not be the case. So if we just go to Micrograd, and you'll see that there's only 2 files here in Micrograd. This is the actual engine. It doesn't know anything about neural nets, and this is the entire neural nets library on top of Micrograd. So engine and neural nets library. This is the actual engine. It doesn't know anything about neural nets, and this is the entire neural nets library on top of Micrograd. So engine and nn.py. So the actual backpropagation autograd engine that gives you the power of neural networks is literally 100 lines of code of like very simple Python, which we'll understand by the end of this lecture. And then nn.py, this neural network library built on top of the autograd engine, is like a joke. It's like we have to define what is a neuron, and then we have to define what is a layer of neurons, and then we define what is a multi-layer perceptron, which is just a sequence of layers of neurons. And so it's just a total joke. So basically, there's a lot of power that comes from only 150 lines of code, and that's all you need to understand neural network training, and everything else is just efficiency. And of course, there's a lot to efficiency, but fundamentally that's all that's happening. Okay, so now let's dive right in and implement Micrograd step by step. The first thing I'd like to do is I'd like to make sure that you have a very good understanding intuitively of what a derivative is and exactly what information it gives you. So let's start with some basic imports that I copy-paste in every Jupyter notebook always. And let's define
What is a derivative is a thing that we need to understand.
function, scalar valued function, f of x, as follows. So I just made this up randomly. I just wanted a scalar valued function that takes a single scalar x and returns a single scalar y. And we can call this function, of course, so we can pass in, say, 3.0 and get 20 back. Now, we can also plot this function to get a sense of its shape. You can tell from the mathematical expression that this is probably a parabola. It's a quadratic. And so if we just create a set of scalar values that we can feed in using, for example, a range from -5 to 5 in steps of 0.25. So axis is just from -5 to 5, not including 5, in steps of 0.25. And we can actually call this function on this numpy array as well. So we get a set of y's if we call f on axis. And these y's are basically also applying the function on every one of these elements independently. And we can plot this using matplotlib. So plt.plot x's and y's, and we get a nice parabola. So previously here we fed in 3.0 somewhere here, and we received 20 back, which is here, the y coordinate. So now I'd like to think through what is the derivative of this function at any single input point x, right? So what is the derivative at different points x of this function? Now, if you remember back to your calculus class, you've probably derived derivatives. So we take this mathematical expression, 3x squared minus 4x plus 5, and you would write it out on a piece of paper and you would, apply the product rule and all the other rules and derive the mathematical expression of the great derivative of the original function. And then you could plug in different x's and see what the derivative is. We're not going to actually do that, because no one in neural networks actually writes out the expression for the neural net. It would be a massive expression. It would be, thousands, tens of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just this kind of thousands of terms. No one actually derives the derivative, of course. And so we're not going to take this kind of like symbolic approach. Instead, what I'd like to do is I'd like to look at the definition of derivative and just make sure that we really understand what the derivative is measuring, what it's telling you about the function. And so if we just look up derivative, we see that, okay, so this is not a very good definition of derivative. This is a definition of what it means to be differentiable. But if you remember from your calculus, it is the limit as h goes to 0 of f of x plus h minus f of x over h. So basically what it's saying is if you slightly bump up, you're at some point x that you're interested in, or a, and if you slightly bump up, you slightly increase it by small number h, how does the function respond? With what sensitivity does it respond? What is the slope at that point? Does the function go up or does it go down, and by how much? And that's the slope of that function, the slope of that response at that point.
Here he says, what does it mean when we ask what is a slope of a function? Okay, I'll watch this till 20 minutes, okay, and gather this sort of unexplained concepts or terms, okay, and then we'll research each of them individually.
And so we can basically evaluate the derivative here numerically by taking a very small h. Of course, the definition would ask us to take h to 0. We're just going to pick a very small h, 0.001. And
Till now, I'm understanding because I do have some idea about what is all of this mean. What does all of this mean? I have watched some of the videos before. It is basically telling that it is basically telling that what happens, let's say x equals to 3, okay, x equals to at x at x equals to 3, the function's value is suppose uh a, okay, I'll be repeating this. At x equals to 3, the value of that function is a. So what does actually finding the derivative of this function means is that if we increase if we increase the value 3 at through very small margin, let's say 0.01, 0.001, let's say 3.001, then what will be the value of f of x? Means then what will be the value of f of x at x equals to 3.001? Okay, so we'll compare both the results, that is the result at x equals to 3, the result at x equals to 3.001, and then we'll measure the differences. Okay, if I increase the value of x, how this function is, how this function is behaving, is it increasing or is it decreasing or is it staying constant? That is what we want to that is what a differentiative, that is what a derivative means. Okay, I only have this much of clarity, but let's see, we'll research this in this episode only. Okay, this is the episode in which we'll dive deeper, we'll go very deep, and get to the crux of what does it actually means.
let's say we're interested in point 3.0. So we can look at f of x, of course, as 20. And now f of x plus h. So if we slightly nudge x in a positive direction, how is the function going to respond? And just looking at this, do you expect f of x plus h to be slightly greater than 20? Or do you expect it to be slightly lower than 20? And since this 3 is here, and this is 20,
Greater.
if we slightly go positively, the function will respond positively. So you'd expect this to be slightly greater than 20. And now by how much is telling you the sort of the strength of that slope, right? The size of that slope. So f of x plus h minus f of x, this is how much the
Okay,
function.
so he tells here the strength of the slope. Okay, he uses this words. Okay, it's very important. What does it actually means when someone says the strength, S-T-R-E-G-H-T, strength of the slope or the response of the slope? We can say response is understood.
Responded in the positive direction, and we have to normalize by the run, so we have the rise over run to get the slope. So this, of course, is just a numerical approximation of the slope, because we have to
Normalize rise over run.
make age very, very small to converge to the exact amount. Now, if I'm doing too many zeros, at some point, I'm going to get an incorrect answer because we're using floating point arithmetic, and the representations of all these numbers in computer memory is finite, and at some point we get into trouble. So we can converge towards the right answer with this approach. But basically, at 3, the slope is 14. And you can see that by taking 3x squared minus 4x plus 5 and differentiating it in our head. So 3x squared would be 6x minus 4. And then we plug in x equals 3. So that's 18 minus 4 is 14. So this is correct. So that's at 3. Now, how about the slope at, say, negative 3? What would you expect for the slope? Now, telling the exact value is really hard, but what is the sign of that slope? So at negative 3, if we slightly go in the positive direction at x, the function would actually go down. And so that tells you that the slope would be negative. So we'll get a slight number below 20. And so if we take the slope, we expect something negative 22. Okay. And at some point here, of course, the slope would be 0. Now for this specific function, I looked it up previously, and it's at point 2 over 3. So at roughly 2 over 3, that's somewhere here, this derivative would be 0. So basically, at that precise point, if we nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case. So we're going to start.
Okay. So what he's telling is at 2 by 3, that is 0.67, at x equals to 0. How much? 0. Yeah, 67. Yeah. So at x equals to 0.67, the function, the slope is coming as 0. Means if we increase this, I didn't get it, bro.
Here, this derivative would be 0. So basically, at that precise point,
At 0.67 point,
at that precise point, if we
yeah,
nudge in a positive direction, the function doesn't respond. This stays the same almost. And so that's why the slope is 0. Okay, now let's look at a bit more complex case.
at x equals to 0.67, the slope comes to be 0. That means that means that that means if we increase x by 0.001 by 0.001, then also the slope will be 0 only. I don't know. We'll ask GPT. We'll ask GPT.
So we're going to start, complexifying a bit. So now we have a function here with output variable d that is a function of three scalar inputs, a, b, and c. So a, b, and c are some specific values, three inputs into our expression graph, and a single output d. It is a function of three scalar inputs, a, b, and c. So a, b, and c are some specific values, three inputs into our expression graph, and a single output d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to again look at the derivative of d inputs, a, b, and c. So a, b, and c are some specific values, three inputs into our here with output variable d that is a function of three scalar inputs, a, b, and c. So a, b, and c are some specific values, three inputs into our expression graph, and a single output d. And so if we just print d, we get 4. And now what I'd like to do is I'd like to again look at the derivatives of d with respect to a, b, and c. And think through.
Okay, so when he says derivative of d with respect to a, b, and c, he actually means is the value, how much the value of d gets affected when I do some changes in value of a. That means derivative of d with respect to a. Okay, that is the concept. So whenever someone says that I want to find the derivative of this value to derivative of d to the value of so if someone says that I want to find a value of this variable with respect to this variable, so he's actually telling to find the relation between them between so he's actually telling to find the relation between the two. So if I nudge this, if I increase or do some changes in this, in how much variance this value is changing. Let's say there will be functions that in which if I change the input in this manner, the function will go in this manner. But there will be function that if I change the value of function in this manner, the function may go down. Okay, the function can increase, the function can decrease. All of these things are possible. But why this is important? It is because it is uh, it is helping us to get to know the relation, to get to know the property of this whole connection between two, that how strongly they are binded or how loosely they are binded. This is the beauty of mathematics. Kya baat hai?
Again, just the intuition of what to. And now what I'd like to do is I'd like to again look at the derivatives of d with respect to a, b, and c. And think through, again, just the intuition of what this derivative is telling us. So in order to evaluate this derivative, we're going to get a bit hacky here. We're going to again have a very small value of h, and then we're going to fix the inputs at some values that we're interested in. So this is the point ABC at which we're going to be evaluating the derivative of d with respect to all a, b, and c at that point. So there's the inputs, and now we have d1 is that expression. And then we're going to, for example, look at the derivative of d with respect to a. So we'll take a and we'll bump it by h, and then we'll get d2 to be the exact same function. And now we're going to print
d2
f1, d1 is d1, d2 is d2, and print slope. So the derivative or slope here will be, of course, d2 minus d1 divide h. So d2 minus d1 is how much the function increased when we bumped the specific input that we're interested in by a tiny amount.
H,
And
yes.
this is then normalized by h to get the slope.
Yeah, so I still don't know why we are dividing this by h. I don't know the term. Why we need to normalize 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 the function by the uh value by the increased value, by the tweaked value. Let's say for simplicity, let's consider increased value, by the increased value. Okay, increased or decreased value. Yeah, let's be generalized. Let's not leave anything, any loose ends. Okay, why do we have to what this spell normalize का spelling z होता है? Okay, got it. This is crazy, this is beauty.
So yeah. So if I just run this, we're going to print d1, which we know is 4. Now d2 will be bumped, a will be bumped by h. So
0.001.
let's just think through a little bit
Okay, let me just check.
what d2 will be
Yeah,
printed out here.
yeah, okay, yeah, let's just think. uh should I directly input the values? If I increase, okay, let's just think, guys. Okay, the value of B is 2, value of B is -3, and then it is plus C. Okay, so it is dependent of A and B only. So okay, so value, okay, actually we are increasing the value of 2, so the it will be increased. Okay, so yeah, so the value that is -6. Okay, okay. If it is -6, so it is decrease. It will decrease, bro.
In particular, d1 will be 4. Will d2 be a number slightly greater than 4 or slightly lower than 4?
Slightly lower than 4.
And it's
I
going to
think
tell us
so.
the sign of the derivative. So we're bumping a by h. B is -3, C is 10. So you can just intuitively think through this derivative and what it's doing. A will be slightly more positive, but B is a negative number.
Yeah.
So if A is slightly more positive,
And
because B is -3, we're actually going to be adding less to D.
yeah,
So you'd actually expect that the value of the function will go down.
yeah,
So let's just see this.
yeah. It will
Yeah.
go down.
And so we went from 4 to 3.9996. And that tells you that the slope will be negative, and then will be a negative number because we went down, and then the exact number of slope will be, exact amount of slope is -3. And you can also convince yourself that -3 is the
I still don't understand why we are finding the slope. Okay, मुझे नहीं I'm sorry. I started in, but we'll get to this. We'll get to this. Why finding slope here?
right answer mathematically and analytically, because if you have a times b plus c and you have calculus, then differentiating a times b plus c with respect to a gives you just b. And indeed, the value of slope will be, exact amount of slope is -3. And you can also convince yourself that -3 is the right answer mathematically and analytically, because if you have a times b plus c and you have calculus, and then the exact number of slope will be, exact amount of slope is -3. And you can also convince yourself that -3 is the right answer mathematically and analytically, because if you have a times b plus c and you have calculus, then differentiating a times b plus c with respect to a gives you just b. And indeed, the value of b is -3, which is the derivative that we have. So you can tell that that's correct. So now if we do this with b,
Got it, bro.
we have just b. And because if you have a times b plus c and you have calculus, then differentiating a times b plus c with respect to a gives you just b.
Yeah. differentiating, differentiating, yeah, getting the differentiative of D with respect to A will give us B only. Crazy.
And indeed, the value of b is -3, which is the derivative that we have. So you can tell that that's correct. So now if we do this with b, so if we bump b by a little bit in a positive direction, we'd get different slopes. So what is the influence of b on the output d?
Yeah, let me think of it. See, B is minus, if I can just 2, 2 plus, 2 plus, this, then 12. So, what's the
So
A?
if we bump b by a tiny amount in a positive direction, then because a is positive,
Huh.
we'll be adding more to d,
Yeah.
right? So, and now what is the sensitivity? What is the slope of that addition? And it might not surprise you that this should be 2.
Hmm.
And why is it 2?
Because A
Because
is 2.
d of d by db, differentiating with respect to b, would give us a, and the value of a is 2. So that's also working well. And then if
Beauty.
c gets bumped a tiny amount in h by h, then of course a times b is unaffected, and now c becomes slightly bit higher. What does that do to the function? It makes it slightly bit higher because we're simply adding c.
Yep.
And it makes it slightly bit higher by the exact same amount that we added to c. And so that tells you that the slope is 1. That
No,
will
no,
be
I
the
didn't. No, I didn't get it.
slightly bit higher. What does that do to the function? It makes it slightly bit higher because we're simply adding c. And it makes it slightly bit higher by the exact same amount that we added to c. And
Yeah,
so that tells you that the
0.01.
slope is 1. That will be um, the rate at which d will increase as we scale c.
Okay.
And then if c gets bumped a tiny amount in h by h, then of course a times b is unaffected, and now c becomes slightly bit higher. What does that do to the function? It makes it slightly bit higher because we're simply adding c. And it makes it slightly bit higher too because
Slope means rate at which the function will change. Ah, let me just write this, man. This is a good line. The slope means the rate at which the function will change.
d of d by db, differentiating with respect to b, would give us a, and the value of a is 2. So that's also working well. And then if c gets bumped a tiny amount in h by h, then of course a times b is unaffected, and now c becomes slightly bit higher. What does that do to the function? It makes it slightly bit higher because we're simply adding c. And it makes it slightly bit higher by the exact same amount that we added to c. And so that tells you that the slope is 1. That will be the rate at which d will increase as we scale c. Okay, so we now have some intuitive sense of what this derivative is telling you about the
But
function.
but see, I got it that if I increase C by some amount, then it does have a direct relation with the D. Okay, direct proportional relation with D. So D will also increase at the same rate. That's why it is 1. Oh.
And we'd like to move to neural networks. Now, as I mentioned, neural networks will be pretty massive expressions, mathematical expressions. So we need some data structures that maintain these expressions, and that's what we're going to start to build out now. So we're going to build out this value object that I showed you in the README page of Micrograd. So let me copy paste a skeleton of the first very simple value object. So class value takes a single scalar value that
Okay, I guess, yeah. Let's just stop here. Okay, let's just go through this. What does all this mean? I kind of got to have an idea, but let's just ask GPT. Okay, so the thing is, when we say, when we say, the slope is 1, it means that the slope, I don't know, man. Okay, let's create a new chat. What does all this mean? I'll be lazy this time. What does all this mean? These are again the touch on the fundamental slope and its role in understanding how functions will. Let's break down the simple steps. What is the slope of a function? The slope measures how steep a line is at particular point. Okay. The slope measures how steep a line or curve. Steep means this or this curve. It represents the rate of change of function. Yeah, rate of change of function with respect to changes in input x. मतलब rate of change of function. I'm not getting. I kind of. I don't know. यार. For the slope is given by change in y. This is one. For straight line, the slope is constant and given by change in delta y by delta x. This is called rise over run. The slope changes at different points, so we use the derivative to find the slope at a specific point x. For a curve, the slope changes at different points, so we use the derivative to find the slope at a specific point x. Okay. So the derivative of x represents how much y will change for a very small change in x. Okay. Okay. What does it mean when someone talks about the strength of the response? Strength of this refers to the magnitude of the slope, how steep it is. A larger absolute value of the slope indicates a steeper line, incline or decline. A larger absolute value of the slope, a slope of 0 means the function is flat at that point. Slope of 10 means a small change in x cause a large change in y. Okay. If our slope of the it about the derivative, which means the rate of change of slope. Okay. What does it mean when we arise? Normalization means standardizing the slope calculation so that it's independent of scale of x. For example, if x delta is too large, the slope might not accurately reflect the instantaneous rate of change. By taking the limit x tends to 0, we ensure that the slope is precise. Okay, yeah, that is understood. What happens if the slope is 0 at x equals to, when the slope at point means the function is not changing at that instant, it is flat or on at that point. Then the slope will not necessarily remain 0 unless the function derivative remains 0 in the neighborhood. In other words, f of the x equals to 0 at a neighbor, the function has a local maximum, minimum, or flat region. And the slope may change as you move from it. Why is normal function by the infinite degree? Normalization ensures we are calculating slope again for instant changes rather than for finite rate or other might change in this. Does the slope mean the rate at which the function changes? Yes, the slope represents the rate of change. If the slope is positive, the uh, stationary. Okay, but yeah, I got it. I got somehow, I do get the somehow I do get the clarity. But the thing is, I need more of this. What does it mean when someone's strength of slope? Let's go one by one. This refers to the magnitude of how steep it is. Yeah, with this one. Explain, giving example, and a real world analogy. But see, the thing is, it says that for a straight line, the slope is easier to calculate. Means the slope is delta y by delta x. Okay, it's just coordinates minus the coordinates of the final coordinates minus initial coordinates of y upon the final coordinates of x minus initial coordinates of x. Okay, that is the slope for straight line. But for curves, it is saying that we have to take the derivative. Why? Because the curve, because the curve keeps on changing at every point. So it is fine. It is quite tough to find the slope. That is what it is telling. Okay, so let's just read more. So the slope measures how fast something is changing. It's a way to quantify the relationship between two quantities that depend on each other. Yeah, agreed, agreed. So slope means how fast something is changing. Yeah, okay. For a straight line, the slope is constant, meaning the rate of change is the same everywhere. For example, if you are driving at constant speed of 60 km per hour, then your distance changes uniformly with time x. Okay, yeah, agreed. Agreed. If I'm, let's say, for 30 minutes, I'm driving, let's say there is a 100-kilometer road, and for 30 minutes, I'm traveling at same constant speed of 60 kilometers per hour. Then, yeah, then I'll be, let's just simplify 60,000 kilometers, okay, and 60 kilometer per second. Then every every minute, sorry, 60 kilometer per minute. Then every minute I will be traveling same distance only, because I'm going at same speed. Okay, this is understood. For a curve, the slope changes depending on where you are. Imagine a hill where the steepness varies as you go up or down. I'll go up only. So steepness is first about this, then it was this, then it was this. Okay, okay, okay. The slope at the specific point tells you how steep the hill is right there. Okay. A real world analogy for the slope. Think of the slope as the steepness of a road. If the road is flat, the slope is zero. You are not gaining or losing height. If the road is steep uphill, the slope is positive. You are gaining height quickly. Yes. If the road is steep down, you are losing height quickly. Yes. Okay. Straight road, constant speed. You are driving on a highway at a constant speed of 60 km per hour. Yeah, that is agreed. Here, the slope of the graph will be distance versus time. It is a straight line, that is 60. So for every 60, for every 60 kilometers, the time required will be 1 hour. That is okay. Yeah, so for every 1 hour, you travel 60 kilometers. That is okay. That is because you are traveling at a constant speed. Okay, so you are not losing here. You're not gaining here, you're not losing here. Okay, let me just check. Curved road. Now you are driving on a mountain road. Sometimes you are accelerating. Okay, slope increases. Sometimes you are slowing down, slope decreases. At any specific moment, your speedometer shows your speed. That's like the slope at that point on the distance versus time graph. At any specific moment, okay, so sometimes you are accelerating. Yeah, bro. Slope increase matlab you slope increase means you will gain height. Slope decrease matlab you will lose height. Okay, so okay. Okay, I need some more explanation on this. Strength of the slope. Strength refers to how steep the road is at a point. A gentle incline is like a small hip has a small hill has a small slope. The analogy, a gentle incline is like a small hill and has a small slope. A steep incline is like a mountain and has a large slope. Large slope means you'll require more acceleration. Large slope means you will require more acceleration. Uh, it will be tough for you to increase to achieve height. For on a gentle hill, walking 1 meter forward might raise you only zero point 0.1 meters vertically. On a steep hill, walking 1 meter forward might raise you 1 meter vertically. Yeah, that is correct, man. If there's a graph and I have two hills, one is this and one is this, and if I walk, okay, so let's just draw here. Let's say I have, see, okay, I have this as a hill, and I have, okay, let me just, I have this as a hill, and I have this as a hill. Okay, so what he is telling us that uh, if I walk this much distance, okay, let's say just for simpler approach, if I walk this much distance, okay, sorry, if I walk this much distance, right? Okay, so the increase in height will be this much only. Are you getting me? But if I, let's say, I'll just, for simpler purpose, I'll just copy this and tell you that similarly, if I, on a steep hill, if I travel this much distance, the increase in height will be, let's just say, will be around this much. You getting me? So this is the, if I compare this two height, if I can just compare these two heights, okay. Oh, yo, this is nice, man. And the distance traveled is same. Yo, what the heck? Hey, what is this, man? Oh, so in both these distances, hey, what the heck is this, bro? So the distance in both of this is same only, but on a steep hill, walking 1 meter will will uh will increase will take you the height much more at much more level. Yeah, this is nice, man. This is nice. And for slower hill, yeah, let me just, this is good, man. This is freaking great, actually. So, a gentle incline in a small hill has a small slope, and the steep incline, like a mountain, has a large slope. Means, for example, on gentle hill, walking 1 meter forward might raise you zero point 0.1 meters vertically, 0.1 meters vertically. मतलब तेरे को ऊपर मतलब you will be uplifted by 0.1 meters only. Suppose this is a 0.1 meter, 1.1 meter, right? But on steep hill, on steep hill, this is comparatively steep hill. Okay, it has more. It is not closer to the ground. It is quite steeper than this one. So on that steeper hill, if you travel 1 meter forward only, same as 1 meter, okay, this is same as 1 meter, then you will get the height, the increase in height is more, obviously more than this, okay. So that is why it is telling us that this is the strength of the slope. Okay, so it is, okay. Okay, so with this expression only we can find, suppose, let's say, guys, guys, suppose I have a different graph here where this is a line, okay, and there is some another line. There is some another. Let's compare this as a real world scenario. Okay, uh, what we can do here is, Okay, what we can do here is, suppose you are blind. Okay, you are not able to see this line or this line, this line or this line. Okay, you are not able to see. But still, if you want to find the difference, if you want to know which line is steeper, then you can calculate by this method. No, let's say I'm a blind person. Okay, let me just write it in a very clear way. This is a line. Okay, this is a line. Okay, suppose let's take this is a mountain, or and this is a mountain. Okay, this is one, this is two. Okay, hey, I cannot change this or what? But this is in meters. Okay, this is the feet. Okay, so let's say you are blind and you are traveling zero point 0.5. Okay, that is somewhere here 1.5. Okay, you have traveled this much meter. So the value feet that you would have climbed here is, let's suppose 1.8. Okay, you still don't know the steep, which you have to find the steeper curve, right? So that is mm, so I need to find this. No, let's just suppose that it is 1.5 only. You increased by 1.5. This is just because this is happening because we have not differentiated these values by proper uniform values, right? So let's say you are getting here only 1.5. Okay, this only. So the slope here will be zero point 0.5 minus 1 upon 0.5 minus 1. That is 1, right? Slope is 1. Similarly, if I increase here to 3.5, 3.5, let's say here, and this value comes up to this, some sort of this one, right? Let's say it is 2.5. Okay, so here the slope will be delta y. Delta y is 2.5, 2.5 minus 1.5, right? Because the value of Sorry, 1, not 5, because the value of y is 1 only. We have taken it from, it's kind of hard to represent all of this, but let me just put it this way only, similar to this height. Yeah. No, this much only. Okay. So the value of y will be 2.5. This is 2.5 minus 1 and upon this one 3.5 minus 3. 3.5 minus 3, that is 3.5 minus 3. क्या वैल्यू आएगी इसकी? Is 1.5 by 0.5, right? That is 3, right? So the slope value of this is 3. The slope value of this is 1. Comparatively, this value is higher than this. So you can derive that this slope is much steeper at as compared to this. Means it can also change. It can also means that this, acha, that the rate of changes in this hill will be more, the rate of change in this hill will be more than this. Why? Because the value of slope is more than this one. Okay, I am still, yeah, I quite understood this, but still I need to. Ah, I need some time, bro. Okay, now the response of slope refers to how the slope itself changes as you move along the curve. Mathematically, this is captured by second derivative. Imagine you are driving up a hill that starts gently but gets, okay, starts gently but gets steeper as you go. The change in steepness tells you how quickly the hill is becoming steeper. If the slope is constant, the response of the slope is zero because the steepness isn't changing. Yeah, how quickly the hill is becoming steeper. On a roller coaster, at the bottom of the slope changes rapidly from negative down to positive. The rapid change in slope creates the sensation of acceleration. Slope doesn't change, so the response of slope is zero. Oh, I didn't know. Slope means how fast something is changing at your speed. How fast something is changing at a specific point, your speed while driving. How fast. Strength, how steep the change is. This one, how steepness itself changes. I didn't understand this. I did not understand this, bro. Understood this. Nope, I didn't get. A 5-year-old is very very small. 10-year-old. Tell, keep the example uniform from across slope across what is slope, what is strength of slope, and what is response of slope. Exercise table. Okay, let's stick to one simple example, a bicycle ride on a hill, and explain everything step by step like we are talking to a 10-year-old. Bicycle ride on a hill. Okay, there's a hill and there's a bicycle ride. Okay, what is a slope? Imagine you are riding a bike up and down hills. The slope is how steep the hill is at that point. Okay, if the hill is flat, the slope is zero because you are not going up or down. It's easy to ride. Ah, acha. Yeah. If the hill is going up, means the slope is positive because it's harder to ride. You need more acceleration to overcome it. Yeah. If the hill is going down, the slope is negative because you are going, it's easier to ride. Yeah. The slope tells you how much higher or lower you will get for every step forward you take. Hmm. What is the strength of the slope? Now imagine you are on hill that gets steeper as you go. The strength of the slope is how steep the hill is. A a big slope means you need, a small slope means the hill is gently slanted. You don't need to pedal very hard. Hmm. A big slope means the hill is very steep. You need to work a lot harder to keep moving. Yes, moreover. For example, if you are climbing a tiny hill where the slope is 1, moving forward 1 meter will make you 1 meter not too hard. Slope is 10, moving forward makes you climb 10 meters. That's a very steep and much harder to ride. Yeah, yeah. Similarly, in this example, climbing this hill will be much tougher than this because the slope here is 3 as compared to 1. Okay. What is the response? This response is how the steepness of the hill changes as you move. Imagine you are riding up a hill that starts from but gets steeper and steeper as you go. Yeah. At first, but after a while, you notice it keeps heading, and that's the response. It's how the steepness changes. Another thing is stay the same, and the response is zero, nothing. So, bring it all together. How to still, yeah, let some riding on a with the 5 means for everyone you climb. Okay, how steep the hill is at any point. Riding on a hill with a slope of 5 means for every 1 meter forward, you climb 5 meters up. ये पता चला मुझे कि slope of 3 means that for every 1 meter, for every 1 meter forward, you will, the altitude will increase by 3 meters up, or the altitude will increase by 5 meters. Strength of slope means how strong the slope is. A hill with a slope of 1, acha, yeah, 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 yeah. Response, how steepness as you go. If the hill starts flat steeper, the response because steepness is increasing. Yeah, this is understood, man. Riding on a hill with a slope of 5 means, okay, we have the timer has reached 0. Yeah, okay. So for every 5 meters, okay, so for every 1 meter, you will go स्लोप का मतलब ये होता है. But now then, how it is related to derivative that we need to think of. Anyways, guys, this is done. The 1 hour is complete, and we shall come back tomorrow. I guess we can continue today. Oh, yeah, we can continue, bro. Um, how the steepness changes as you go. How steep the hill is at any point. Riding on a hill with a slope of 5 means for every 1 meter forward means for every 1 meter forward you climb 5 meters up. मतलब वो तो समझ में आ गया मुझे इसलिए. Okay, okay, now combine this hill example. Now frame this hill example as a question in mathematics which revolves around the concept of slopes. Sure, here's a math question based on a hill. Okay, you are riding a bike on a hill. The height of hill at any point is given by the function 2x square minus 3x plus 5, where hx is the height of hill in meters and x is the distance you have traveled forward in meters. Okay, so what is the slope? Okay, 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 yeah, this is good. This is how we are going to solve. So you are riding a bike on a hill, and the height of the hill h at any point is given by the function. Matlab there is a function. Let's say you are going to. Okay, okay. Let's just do this here only. So there is a hill. Okay, this is a hill, right? The height at any point means this is the ground level. Okay, okay. This is the ground level. Now the height. This is the height. The height of hill at point this is given by the function 2x square minus 3x by 2x square minus 3x plus 5. Okay, and this is at uniform point. Matlab means that at this point also the hill the height of hill is given by this function only 2x square minus 3x plus 5, right? Okay, so where h of x is the height of the hill in meters. Yeah, this is h of x is the in meters. Yeah, at and x is the distance you are traveled forward in meters. Yeah, okay. So x is the distance. X is the distance. This x, no. Yeah, this x is the distance. This x. Let me just write it here. This x is the distance. Okay, इसको हम let's say take this as h1. This is at h2, height at point 2, height at point 1. This is at x1, and this is at x2. Okay. Now What is the slope? Slope means ये पॉइंट पे व्हाट इज द स्लोप एट x इक्वल्स टू 1, मतलब स्लोप का मतलब क्या हुआ कि मतलब ये पॉइंट पे ढलान कितनी है, ठीक है, एट x इक्वल्स टू 1, देन इट इज 2 माइनस 3 4 2x स्क्वायर माइनस 3x प्लस 5, नहीं मतलब व्हाट इट इज टेलिंग इज, it's for short name, I don't tell me. Find the slope of hill, the steepness at slope मतलब ऊपर क्या हमने पढ़ा था, let us just slope ये है ना, let's just paste this because this sentence has clicked something in us. Slope means riding on a hill with slope of 5 means for every 1 meter forward you climb 5 meters up. Uh, so when it is asking here that what is the slope at x equals to 1, means it is telling us that how much, by uh, how much percentage the height will increase at x equals to 1, right? Let me just check. So you are asking here, ah, so indirectly here you are asking that uh oh wait a minute guys. Yeah. So here indirectly you are asking that how much the hill has okay, by how much, by how much the hill has increased the height, increased slash decreased the height at x equals to 1 meter, right? Yeah, you got it. When we ask for the slope of hill at x, we are asking how much the height of the hill increase or decrease for a very small step for at x equals to 1 meter. Exactly what the slope or derivative tells us that the rate at which the height changes as you move for along x. No, no, I'll calculate, my boy. I calculate it for you. Okay. So when it is telling us here that find the slope of hill at x equals to 1 meter, it is telling us that how much the hill has increased itself or decreased itself. Okay, so the value it needs to get abhi now if I say, let's say the point is here, okay, and this is not a steep line, obviously this is some sort of parabola curved line ही लग रही है, right? Okay, so if I can just value at 2 minus 3 plus 5, that is minus 1 4. So the 4, if the slope is positive, the hill is going 4. Yeah, okay, let me just 2x square sigma minus 3x plus 5, calculate the derivative from simple symbols to that is. Yeah, we just have to go derivative, that is 4x plus 5, that is 4 minus 4, huh? Huh? 4 minus 3, that is 1. Okay, but एक minute, just a thing. Differentiation h equals to calculate derivative differential, ये तो इसने कर दिया डायरेक्ट अपने इससे. नहीं, we are missing here something. उसने डेरिवेटिव ले लिया इसकी at x equals to 1, at x equals to 1. No, I'm not able to get this. At x equals to 1, I don't know. If the slope is positive, yes. When we ask here how much the height of the hill increased degree for a very small set x equals to 1. How the, oh, acha, is it telling like this? Like, oh, is it telling like this or what? Let's say in this only, right? Here, this is a point x1, and this is the point x2, right? And the difference is between 1. So if we travel this 1 in this 1 meter, by how much height, by how much height the hill is increased? This, this. Okay, guys, I need to close down this. I need to shut my camera. Just wait a minute. Actually, what we need to do is I'll just close this for I'll delete this video capture, right? I will I'll add this window capture, video capture. Now you guys might be able to see. Obviously, quality is very, very bad, but bear with me, guys. Bear with me. Okay, let me just plug in this my charger. Yeah. So basically, here we are telling this how much by how much is increasing or decreasing. But does it mean so if I say that for at this point where x equals to 3, the hill is changing this much amount of height. Should I do this? Yeah, let me ask. If the other space running around constant, you're likely trying to analyze how to slow down. The worst is how slow the direction point, however, then yes. If your goal is the house slow, you will find identity. Yes. So at x equals to 1, at x equals the slope seems steep upward, meaning the function is increasing slightly. At x2 the slope might still be upward, that is, at x equals to the slope might be flat. Okay, so we can interpret the value of we can interpret how the hill is going. Interpret the results at x as a 7 and you're going at x positive. Okay. Real life and you're going imagine riding your bike at so you're going down. Start climbing gently up. Yeah, yes. So it is telling us, that, yeah, this I understood, but see, in a way, we have the slopes here were derived by taking the derivatives, okay? But why the slopes here were calculated taking a derivative? Change in height minus change in डिवाइड को करने का और को हाँ उतना डिस्टेंस में ना भाई उतना डिस्टेंस तो पर डिस्टेंस कितना करना चाहिए हाँ इसीलिए तो करना पड़ेगा ना डिवाइड एट लिमिट एक्स अच्छा डेल्टा एक्स बहुत स्मॉल है अच्छा अच्छा so here it is telling okay if there is a straight line and the slope is ये फाइंड करना है स्लोप मीन्स इंक्रीज हुआ है डिक्रीज हुआ है या कांस्टेंट है ठीक है दैट इज डेल्टा वाई बाय डेल्टा एक्स हाइट में इंक्रीज हुआ है तो एक्सेलेरेटर बढ़ेगा डेल्टा वाई बाय डेल्टा एक्स नो yeah but for this यहाँ पे it's tough because x यहाँ पे मैंने ले लिया और मैं यहाँ कर लूँ और मैं ऐसे करके लूँ तो यहाँ पे देखा जाए तो ये पहले थोड़ा डाउन है फिर एकदम से ऊपर हुआ है तो वो नहीं वर्क करेगा तो इट इज गिविंग अस एट दिस ओनली कि ये पॉइंट पे इतना मैं मतलब कितना मिल गया दिस मच स्लो एट एक्स डेल्टा एक्स टेंड्स टू 0 तो इसका वैल्यू क्या Why both are great, bro. Both are great. But this is done. Okay, this is done. So, yeah, I do get to know that why we are taking derivatives because we want to find. Okay, now this is done. But now, okay, understood. But now I want to know how do mathematical expressions are derived derived for a function. Like in the previous example of a hill, you said height of hill. Yeah. So the first step is to understand the behavior of what you are trying to describe mathematically. For the hill example, the hill rises and fall, meaning it isn't a straight line. Mm. It has peaks and valleys, so its slope changes at different points. Slope changes. The hill's height depends on the distance along its base x. So we need a function that relates. the height h of x to x. This behavior says we need a non-linear function that can model change or change typically in one powers of x. Choosing the right type of function. To model the hill, we choose a polynomial function because polynomials are flexible and can represent curves with fixed and flat direction. The degree of polynomial determines how many turns that the curve can have. A straight line y equals to mx plus b has no turns. A quadratic equation is y equals to ax squared plus bx plus c can have one peak or one valley. Can have one peak or one valley. A cubic ax cube plus bx plus c can have two turns, making it ready for a hill that rises, flattens, and straights. For our hill, a curve is good because it can naturally capture the shape of rising. Connection data of if the hill exists around, we could collect measurements, measure the height of the hill at several points along with base x. Then is to tell the exit equations. Constructing the function. Using the observations, we determine the coefficients of polynomial ABC that satisfy the data point. These are to form the curve fitting system of equations. Using tools like regression, we fit a cubic equation takes to our data. The method calculates the best data and the error between the actual data and predicted values. Okay. Curve fitting. Okay. Substitute the data points into polynomial this plus t h of 0 uh, h of 0 so this is trying to find ABCD or defining अच्छा Upward to downward. Eh? A turn refers to a point on a curve where the slope changes direction. Hmm? Hmm. Upward to downward or downward to. Okay. This time. हमें पानी आयो हमें पापा पानी आयो sorry guys but now I want to ask here is that roots what does the roots of a quadratic equation means? Here it is said that the root of derivative of polynomial are the points where the slope is zero. Yeah, that is agreed. Where because there's a flat section, then only it will start. And the slope is where the graph is momentarily flat. So the number of real roots of the derivative determines how many times the slope becomes zero with direct answer. Acha. And the derivative of this is 3 minus 6 equals 2. So Doesn't matter as आलू से. Okay, guys, I'm stopping this now. Okay, we'll continue from this in next day. Bye, guys. Bye.